All right, let's dive right in. Today, we're heading into the high-stakes, almost invisible world of digital forensics. You know, a world where the most crucial evidence can just vanish in the blink of an eye.
So I want you to picture this. You're an investigator, right? You just arrived at a crime scene. But forget fingerprints and footprints. This scene is digital. So what's the first thing to disappear? I mean, what's the one clue you could lose forever, right at that very moment?
Well, it turns out the most critical clue is the one you can't even see. It's ephemeral, it's fleeting, and it's ready to disappear in an instant. And that is the core challenge we're tackling today.
And this really highlights a huge contrast, right? I mean, think about physical evidence. It's pretty stable. A weapon left at the scene, it's going to be there hours later. But digital evidence, it's more like writing in the sand. It is so fragile, so dynamic. Parts of it can literally disappear in less time than it takes you to unplug a computer.
Which brings us to our first big idea here. In digital forensics, every single second counts. You've got investigators in this constant high-stakes race against the clock.
Yeah, and here's the kicker. There's this idea, kind of like the Heisenberg principle, but for digital forensics. The basic gist is that the very act of looking for evidence, running a command, peeking into the memory, can actually change or even destroy the very evidence you're trying to find. So the challenge isn't just finding the clues, it's doing it while leaving the lightest footprint imaginable. It's a real balancing act.
So, how on earth do investigators navigate this digital minefield? Well, they have a kind of master key. It's a guiding principle that dictates every single move they make.
And that principle is called the Order of Volatility, or OOV for short. Think of it as a rule book for collecting evidence. It's all about prioritizing based on how fast that data is going to disappear. In other words, it's digital triage.
And the golden rule here is so simple, but it's absolutely non-negotiable. You collect the most volatile stuff first, the most stable stuff last. You have to rescue the data that's about to vanish before you touch anything else. Everything, and I mean everything, flows from that one simple command.
Okay, so to really get our heads around this, let's look at a visual. We're going to call it the volatility ladder, and it breaks down just how fast different types of data can, disappear. And just so you know, the scale we're talking about here it's absolutely staggering. We're literally going from data that lasts for mere nanoseconds, all the way to data that could potentially outlive every single one of us.
All right, let's climb this ladder together. At the very, very top, the most volatile stuff, you've got CPU registers and caches. That data, it's gone in nanoseconds. Seriously. Just below that, you have RAM, the computer's short-term memory. That's where active programs and, crucially, maybe even encryption keys are just hanging out. A little further down, you've got running processes and the network state. And then, way, way down at the bottom, you find the really stable stuff. Think hard drives, SSDs, and, even good old-fashioned printed documents. That stuff can hold data for decades, even centuries.
I mean, let's just stop and think about that for a second. A nanosecond. That's how long you have to capture what's going on inside a computer's processor. It is an almost impossibly short window of time.
And then on the complete opposite end of that spectrum, you've got data stored on things like ROM chips. That stuff can last for centuries. This incredible range from nanoseconds to centuries is exactly what investigators are up against every single day.
Okay, so knowing about the ladder is one thing, but actually using it in the field, that's a whole other ballgame. And the very first question an investigator asks when they get on site is a really critical one. Is this computer on or is it off?
And this right here, this is the investigator's dilemma. Because if the system is live, if it's running, all that super volatile evidence, the good stuff, is in its RAM. You pull that plug and poof, it's gone forever. But if the system is dead, powered off, all the evidence is sitting on the hard drives. If you power it on the wrong way, the boot up process itself could overwrite the very clues you're looking for. No pressure, right?
And believe me, these mistakes are catastrophic. Pulling the plug on a live machine is the classic rookie error. You just wiped out all that crucial live data. But it's not just computers. Think about a mobile device. One simple mistake, like forgetting to stick it in a Faraday bag to block all signals, could be all it takes for a suspect to remotely wipe that entire phone clean. Just gone.
So, okay, let's say the investigator makes the right call. What's next? How do they make absolutely sure the evidence they collect is pure, untainted, and admissible in court? How do they preserve that pristine digital fingerprint?
Well, it all comes down to following 4 fundamental pillars of integrity. Number 1, you never work on the original evidence. Ever. That's rule number 1. 2, You use a special piece of hardware called a write blocker that physically prevents any changes from being made to the original drive. 3. You create a perfect bit-for-bit clone of that original drive. And 4, this is a big one, you use 2 different tools to verify that your copy is perfect, just to make sure your own software isn't messing things up.
But wait a minute. How can you actually prove the copy is perfect? I mean, really prove it?
The answer is something called a cryptographic hash. The easiest way to think about it is like a unique digital fingerprint. It's a math problem, basically. You feed the original evidence into this function, and it spits out this long, unique string of letters and numbers. Then you do the exact same thing to your copy. If those 2 fingerprints, those 2 hash strings, match perfectly, you have mathematical, scientific proof that your copy is identical. But if even one single bit is different, just one, the entire hash value changes completely. This is the absolute bedrock of digital evidence integrity.
Now, I know all these rules and procedures can sound a little abstract, so let's bring it back to the real world. Let's look at a case where one small mistake had absolutely devastating consequences.
Okay, so this is basically a case study in what not to do. Picture a murder investigation. A first responder arrives on the scene and finds the suspect's phone. I mean, this thing is a potential goldmine of evidence, right? But a single, simple error in judgment is about to change everything.
So here's what went down. The officer, probably just trying to be helpful, starts guessing passwords to try and unlock the phone. But after too many wrong guesses, the phone's security protocol kicks in and does exactly what it's designed to do. It completely erases itself. It's a full wipe. All of that potential evidence, texts, photos, call logs, you name it, gone. Forever. And you can bet what happened in court. The defense argued, pretty successfully, that the police themselves had destroyed crucial evidence. It cast a huge shadow over the entire investigation.
And this really brings us to a final, pretty sobering thought. When the most important clues in a case can be erased just by pulling a plug or by guessing one too many passwords, you have to ask, how fragile is the truth in our digital world? Is justice itself just one power cycle away? It's a huge question, and it really shows why understanding the order of volatility isn't just some technical skill, it's absolutely essential for justice itself.